All right, yeah, so thanks everyone for coming, and special thanks to the organizers for putting on a very nice and very diverse set of topics workshop. So this talk will move a bit back towards the NISQ side of the DINISQ. And I'm going to be talking about some small-scale algorithms that we've been running on Quantinuum's trapped ion quantum computer. And the idea will be to use tensor network representations of quantum states to reduce the size of the quantum memory you need to do interesting simulations. And the key capability that we're going to take advantage of in this system is that it's possible to do high-fidelity mid-circuit measurements selectively on some qubits without affecting others. And we're going to use this to do a sort of quantum data compression utilizing these tensor network representations. And I want to stand on a soapbox for a second, and hopefully I'll convince you by the end of the talk that mid-circuit measurements, which is something people have thought about for a long time as part of error correction, maybe some long-term goal on the way to fault tolerance. You're going to need to develop these. I hope to convince you that they'll actually be quite useful for practical NISQ applications. And it will encourage the experimentalists in the audience to think about how to do them well in their systems. Okay, so the kind of motivation I have in mind is simulating something like a lattice model of interacting electrons or spins, which I think is a natural target for doing practical things with a quantum computer. And in the normal way of simulating these systems, you would take basically each active orbital in your system, encode its occupation number onto a qubit, and you can basically simulate the number of orbitals that you have qubits worth. So you could ask, how many qubits would you need to beat the classical state of the art on a similar problem? And the answer is a bit depressing on first look. So it's kind of routine now to do simulations of hundreds or thousands of site lattices with classical computers using tensor network methods, whereas it's very hard to imagine building a functional computer with 1,000 qubits. Okay, and then the reason why these classical algorithms are so efficient, which I'm sure is familiar to many of the audience, is that the states you're describing are not random states in Hilbert space, but they're highly structured states, like low energy states of local Hamiltonians, or things that you get from them by short-term time evolution. And these tend to have a lot more local and a lot less entanglement than a random state you pull out of your hat from Hilbert space. So for example, in one dimension, you can use this to write your state as a matrix product state, which I won't review in detail, but the key idea here is that in addition to representing physical degrees of freedom, which are these kind of legs sticking out on the vertical length, you also introduce auxiliary bond degrees of freedom that encode correlations and entanglement between the sites. And the memory cost here grows with the size of this virtual bond space, in particular the bond dimension, which I'll denote as chi, and very roughly you need the bond dimension to be exponentially in the entanglement that you get between the two halves of the system separated by cutting this bond. So for example, in 1D, for gap states, this entanglement is constant, and you can get infinite system simulations with a constant amount of classical memory. It becomes harder to do these things in 2 dimensions, but it still helps you to represent states in this way. For example, with 2D DMRG, you can simulate, say, like 10 or 20 by infinite systems routinely with this kind of representation. So what I want to do here is to try to see if we can take advantage of the same structure for quantum algorithms and to use quantum circuits to generate the tensors in these tensor networks and to simulate systems that are kind of much larger than you can store all at once in quantum memory. And I'll show you a couple very NISQ demos where we certainly won't bound any errors or prove any theorems, but we can show some examples that all have the flavor of simulating, let's say, 40 or 50 site spin or electron systems with just a handful of qubits. And I'll also show you how you can do things beyond preparing low energy states of this system that approximate ground states, but also simulate in an unbiased way dynamics. Okay, so how would you prepare a quantum tensor, or a tensor network on a quantum computer? So the way I have in mind, and then I'll talk a bit about what restrictions this imposes on the tensor network, is to take your tensor, which has bond degrees of freedom and physical degrees of freedom, and to imagine encoding the spaces of these bond and physical spaces into the Hilbert space of some qubits on your quantum hardware. So I'll introduce qubits to represent one of the bonds and qubits to represent the physical site. And the tensor I'll implement by, if this tensor satisfies specific constraints, in particular it's an isometry from its input bonds to its output physical and bond space, then I can actually encode this into a block of a unitary matrix that I can try to implement as a quantum circuit. So you'll notice here that basically this tensor has more outputs than inputs, which is something you normally can't do with a unitary operation. To make up for this, you just inject the missing inputs in some fixed reference state. Let me call it 0. Okay, so how do we actually do a computation in this way? The idea would be, if you start with your bond and physical states on this site, run them through the circuit, what it's going to prepare is the physical state on the output of this site and the bond of the next site over. And so to prepare a full chain, and we'll show another picture of this in a bit, you would just kind of iterate this procedure, bringing in a fresh physical qubit for each site, and your bond site would just kind of read out some information about the state of the system at that site and kind of move on. So one kind of nice thing you might notice here is that you actually don't need an independent qubit for every site in your chain, because once you measure the site, it never participates in any of the future circuits. So you can just measure it and reset it to 0 if that's something your hardware allows, and reuse it for the next site. And so in principle, all you need is enough qubits to represent one bond and one site of this matrix product state, and you can represent an infinite system, assuming your bond dimension permits you to describe the state of that system. Another thing I want to say is that you can sample the things you'd normally care about sampling, like correlation functions. Even there may be some ways to measure entanglement that I could talk more about if you're interested. And there's no additional sampling overhead for doing it. There's no need to post-select or do anything. You just have the normal sampling cost for these things. So how does this work? So suppose you wanted to measure, say, the correlator of like the Z operator on site 3 of some chain and the X on site 1. So what you do is, prepare some initial state of your bond qubits that corresponds to the left boundary conditions of your chain. You'd run your circuit that is a block encoding of these tensors. And since I'm interested in the X value on the first site, I would then measure the physical qubit in the X basis, record that outcome, reset it to 0, and then repeat this. On the second site, I'm not measuring anything, so I would just measure in whatever basis and disregard that information, the physical qubit. Reset it to 0, proceed, measure in the Z basis. And then, in principle, I could keep going down the chain and measure whatever correlations later in the chain that I want. In practice, actually, you can see that all these future results won't impact this correlator, so I could just stop here when I'm done, actually. Yeah, so this is kind of the basic idea of the whole rest of the talk, so let me just stop now and ask if there are any questions. Yeah.
I apologize if this is an ignorant question, but what does the physical implementation of quantum hardware currently look like?
Yeah, let me put a pin in that, and I'll talk a lot about that. Yeah. The short answer is that, in principle, the bond dimension you can access is the size of your Hilbert space of qubits. It could be very big compared to what you could fit in classical memory. Okay, so kind of natural question is, what sort of tensor networks can we represent in this way? Well, I've shown you how to make a 1D matrix product state. It turns out you can also do a kind of similar thing if you have a tree tensor network or a Mara tensor network, which are nice for describing critical states. They're actually already, the elements in here are either unitaries or isometries. So they're kind of natural for implementing on a quantum device. It's a bit hard to parse at this scale, but you can basically chop up these tree-like tensor networks using a number of qubits that grows with only the depth of the tree, and implement them kind of sideways as this quantum circuit. And I'll show an example of doing this in a little bit. You can also do this in higher dimension, as long as your tensors in your network are isometries. So this brings to another point, like, so what restriction does it place that you have to be able to implement these tensors with unitary gates? And so what it restricts is that the tensors have to be isometries. In 1D, we kind of know this is a mild constraint. You can always put your MPS in canonical form, and then that'll be satisfied. In higher dimensions, I think people are only really starting to probe in the last couple of years what this means, but there are some encouraging results that a large class of states, including even like non-abelian topological orders, just non-chiral ones, can be kind of represented by low bond dimension isometric tensor networks. Yeah, I saw a question there.
A simple question. So in the worst case scenario, we have a lot of entanglement. It doesn't give us anything, right? Because we still have one dimensional still be.
Yeah, so don't do this if you're trying to describe a volume law state with maximal volume law coefficient. But even if you have volume law with less than maximal coefficient, you may save a constant fraction of qubits, for example. And area law is even better. You get kind of a whole dimension's less worth of quantum memory required. Yeah, so when could this beat, in principle, classical methods? Well, the bond dimension, if you have q qubits, can be 2 to the q. And ignoring whether you can actually control this huge space, in principle, this could let you do things that you can't fit in classical memory, but yet with relatively small qubit registers. Yeah, a kind of important question is, we can, in principle, represent large bond dimension tensor networks in this way, but what kind of circuit resources would you require? And we know that to represent a general circuit on this many qubits would require, local gate counts that are also exponential in Q, which wouldn't be good. So maybe a refined question is, if you restrict yourself to, for example, constant or polydepth circuits for each of these tensors, what class of states does that give you? And I can say a little bit more offline if you're interested in, but there are ways to do basically adiabatic state preparation in this method that show that for kind of most states that you can adiabatically prepare, you can get away with no worse than poly system size depth circuits for these tensors. And you may be able to do better. This is just kind of a simple argument. So yeah, I think it's definitely polydepth circuits will generate almost any physical state that you care about. And you can maybe even work on improving the polynomials or working on constants. So let me just show an example. So let's just consider a spin chain where you have a spin half on every site, and we're going to consider the kind of classic transverse field Ising model, which has a quantum phase transition when this parameter lambda is tuned to 1. And I want to sit at that phase transition where you have a lot of entanglement compared to the area law states sitting on both sides. And this system's a bit simple. It's integrable. You can map it to free fermions. You can solve it classically. So let me make life a little bit harder by adding a perturbation that breaks integrability but doesn't disrupt the criticality. And so that, just as a warm-up, I want to, I'll cheat a little bit and say, suppose I know the tensors I want to synthesize to realize this state. So let me just, find, using my favorite DMRG algorithm, some classical representation of this state. And then I'm going to choose a quantum circuit architecture and try to synthesize the gate parameters in that circuit to hit this, this critical state. And then I'll implement that on a quantum computer and see if it works, kind of, just to kick the tires a little bit. So we'd choose one of these Mera-like tensor networks, which are very nice at capturing the kind of scale invariant critical properties. And as I mentioned before, to do a depth D Mera, you need of order 2D qubits in your physical hardware. And so here's some experimental data from the Quantinuum system. where as you increase the depth of the mirror, you can kind of reproduce longer and longer correlations. And this solid line is the theoretical answer from the classical DMRG, and these other things are actual experimental data points. And just to say that you can produce correlations out to, in this case, 32 sites with fairly high fidelity using a noisy 8-qubit system. So I think this is kind of what for me is exciting about this approach is that you can do a lot with very few qubits. And I am optimistic that this will kind of like shorten the path to doing like actual quantum advantage material simulation. Because you don't have to beat DMRG, you just have to have your qubits beat the bond dimension you can get to classically. Yeah.
So here you're just implementing a DMRG or Mera calculated circuit into this quantum circuit.
Yeah.
But how can I see that this can be actually used to obtain the ground state of a certain
hold off on that question.
Oh, okay.
That's the next slide. Yeah, Mohammed.
Translation on invariance was assumed.
You don't need to. It reduces the number of parameters because then every tensor is the same. But in principle, that's not a requirement. I could just do a different circuit for each site. That would give me a non-translation.
So this mapping that you have, that you had this, that you represent that block
right
by a bunch of qubits.
Yeah, so for one site, I do some circuit, and the next site, I change the parameters of my circuit and run a different circuit, and that would give me a non-translation invariant wave function. Yeah, it makes life easier if you don't have to do that. Just number of circuit parameters you have to tune up would be lower, but it's nothing fundamental. Yeah,
Sir, can I ask a similar question about the translation invariance? So you're like talking about a mirror ansatz here, but there's also these ansatz for critical states where you just kind of have like a grid going into the bulk.
Yeah.
And then it would be translation invariant, and you'd be like using these qubits higher up the
hierarchy. We kind of also did things like that. You can maybe check out that paper, but we have plots like that also.
Sorry, just specifying question. As this figure, each point and triangle and circle is just a 2-qubit gate, right?
Yeah, so we just took arbitrary 2-qubit gates here, and the red isometries are missing an input, so you just inject a 0.
So you use some classical knowledge of what.
Yeah, right now I'm totally cheating. I have some classical answer that I'm trying to synthesize. So maybe what do you do if you don't know the answer already? This is a NISQ talk, so I only have one answer. Maybe you guess and you check. So we'll kind of, pick some tunable circuit, measure the energy using this sequential sampling procedure to measure each term in the Hamiltonian, and then classically optimize the parameters and hope we don't, get trapped in some infinite dimensional optimization space or finite but huge dimensional. So does this actually work in practice? So what I'll show you is a kind of a little snapshot of some case study we did of a bunch of models and circuit architectures and things. So it'll be a 2-dimensional Heisenberg model that, like a 6x6 Heisenberg model in 2D. And we're going to represent it as kind of a snake DMRG state. And on each of these tensors, we just chose some circuit that's easy to scale in both qubits and numbers, just say like a brick circuit. And the way, if you just try to optimize this all at once, it kind of fails miserably. But if you build the circuit up layer by layer and use the optimized result from the previous layer to seed the optimization of the next one, maybe with a little randomness and a couple other tricks that we describe in the paper, you can actually optimize large number of parameter circuits without getting trapped in local minima, just empirically. And so what I want to show you is the error in the energy on this kind of Heisenberg model square versus the number of parameters, number of variational parameters in the system. And I'll compare these two quantum circuit generated matrix product states of different number of bond qubits versus kind of classical DMRG calculation. And so one interesting thing we notice is that for this and variety of other problems, the error in the energy goes down as a power law on the number of parameters empirically. And one thing that's kind of interesting is that the power law is steeper than the classical DMRG, which is kind of intriguingly suggesting that there's actually some sparse structure to the tensors that you want to create in here that's not just like treating them as a box of numbers, but is somehow being at least partially captured by a quantum circuit and being taken advantage of. Okay, so if you run any variational calculations on quantum hardware, you know that doing a 1,000-dimensional optimization where you get your data from a quantum processor each time, it sounds like a real headache. Something that would take a century or two to carry out. So one of the really important things I think for making this practical will be to reduce the complexity of variational procedures that you need to get a decent approximation of a ground state. And so one strategy I'll talk about now is to try to start with a good classical guess for the system you're trying to describe. In this case, I'll look at a 1D spinful Hubbard model. So electrons hopping around with local on-site interactions, and the electrons will have spin. And we're going to start with a mean field, like Hartree-Fock ground state of this system, and then try to use that to refine to treat the interacting problem. And you may also do this for other things, like maybe you get a decent DMRG calculation of a ground state, but you don't care about the ground state. You want to know like spectral functions and time-dependent things that you can't calculate easily because time evolution is hard classically. Maybe you could synthesize that ground state on a quantum computer and then use like more efficient time evolution things to do quantum advantaged things. Okay, but let's look at, so there's this kind of cool algorithm by Fishman and White for taking a Gaussian fermion state, maybe like a Hartree-Fock ground state, and rewriting it into a matrix product state. So the main idea is this. So if you look at a free fermion system, the entire correlation functions are all by Wick's theorem dictated by the 2-point correlators. And these 2-point correlators are Green's function. Its eigenvalues are either 1 or 0 in a pure state. And the idea of this Fishman and White algorithm is that if you look in a block of size B in my like entangled free fermion state, if I make B big enough, you usually find an eigenvalue of the Green's function restricted to that block that's very close to 0 or very close to 1. So it's almost disentangled from the outside. And I can do a sequence of rotations on this matrix to isolate that almost completely occupied or almost empty site onto the first site and disentangle it from the rest of the system. And then I can look at what's left and kind of repeat this until I arrive at a product state. And so it's a pretty simple observation that I can turn this procedure into a quantum matrix product state just by reading it backwards. So if I read this backwards, I start with a product state and I output the mean field ground state that I want to get. And the interesting thing here is that, okay, so in this quantum matrix product state, the number of qubits you need in hardware grows as the size of these blocks you need to find an almost disentangled orbital. And the depth per tensor from these rotation matrices is also of order the block size. And empirically, we kind of just did some numerical study for kind of different systems that you care about, like metals or Chern bands or all your favorite free fermion systems. Well, maybe I didn't get all of the favorite ones. But empirically, it seems like if your system's linear size is L, the block size tends to scale as the entanglement entropy for a cut in that system. So it goes as the area in d dimensions. If you have a Fermi surface, there's a log violation of this, and it seems to be logarithmic in 1 over the error that you're trying to. So this is an approximate representation of the state. If you want infidelity to be order epsilon, it's only a log overhead cost to hit that. Okay, so here's just a simple experiment on a 2-leg ladder. It's half filled. It has a two Fermi surface, in 2 1D Fermi surfaces here, so it has quite a bit of entanglement. You can run this procedure using, let's say, 6 qubits to simulate 16 plus sites. You can measure density, or other kind of correlations and actually get pretty good agreement with the state that you want to put in. Okay, so this is kind of step one in solving an interesting problem. So the idea is, like, suppose now I have an interacting fermion system I want to solve. The flow might look like, find the mean field ground state, turn it into a quantum matrix product state, and then add variational parameters that you can tune to try to hit the correlated ground state. So we looked at a couple different ways of adding correlations in. One simple way is to just turn these like free fermion hopping gates that you need for this Gaussian MPS into just general number conserving non-Gaussian gates. And so the results there are shown. This is for half filling. That's this. The mean field is this kind of pale blue line. This like general non-Gaussian gates thing is this dashed blue line. There was an even simpler kind of thing that you can do here at half filling and large U. You kind of approximately get a spin chain type ground state. And so we, taking advantage of that knowledge, we can design like a single parameter variational state that actually, gets you kind of reasonable accuracy, maybe like 10% kind of accuracy of the ground state. I think the important thing to consider here is if you compare to like an unstructured circuit ansatz, shown here in black, you can do better with fewer parameters using this mean field to seed your optimization. Okay, let me not spend too much time on it, but yeah, we also implemented this specific half-filled U equals 4 point on Quantinuum system, and you can measure things like the fact that like spin and charge behave very differently in this 1D system in the ground state. And I think this is actually probably the largest scale calculation of an interacting electron system in a circuit-based quantum computer. And the way we did that is kind of not by making a big system, but just by using few qubits better in this quantum tensor network way. Okay. Yeah, are there any questions? Can you remind me the end time? Is it now, or is it now plus questions? Okay. Yeah.
In the previous section where you were showing the function of the number of parameters, if you had plotted that between the like regular MPS and the sort of block MPS, would they have the same power law?
Oh, interesting. No, I think it'd be much worse because well, okay. It seems to collapse on number of parameters independent of bond dimension, actually. So for the different number of bond qubits, you got almost the same plot, and they would have very different bond dimensions. So I think it wouldn't look good on that plot, I think. Really care about bond dimension, it just cares about circuit complexity. All right, so let me move a little bit faster and try not to keep you from lunch for too long. I just want to mention that you can also, in addition to preparing ground states, if you have a representation of a low energy state and you want to time evolve it, say with some trotterized circuit like this, it's possible to slice up this trotterized circuit along reverse light cones and interpret qubits coming into this dashed line from the left as bond qubits coming in and going out to the right as bond qubits going out. And in addition, you may have like an MPS representation of your initial state shown by this like red bond qubit, and to basically redraw this circuit into a quantum matrix product state form. So here the trade-off you're making is that the number of physical hardware qubits you need grows with the time of the circuit, but not with the size of the system. And this is advantageous, for example, if you have a lot of correlations in your initial state, shown by these like blue correlation regions. And then to measure like a 2-point function after some time t, you may need much more than t qubits to represent this in the kind of ordinary like bottom to top way of running this circuit. Whereas sideways, you would only need order t qubits. Just briefly, you can kind of check this. Just for fun, we took Tomasz's favorite kicked Ising model, which you, in certain limits, can simulate exactly classically, and you get these nice dual unitary kind of behavior. But the algorithm can also simulate non-classically solvable things where, we have non-dual unitary circuits. And we're able to get kind of reasonable quantitative accuracy on like 32 site systems, again, with only a handful of qubits. And let me just wrap up there, actually, since I'm kind of pushing into lunchtime. So thanks a lot for your attention.
One question. Thank you very much for a very nice talk. It's very inspiring. I just want to ask a question. So why is these gates are guaranteed to be unitary? So if it's you generated from this matrices from DMRG, so
yeah, you have to put them in canonical form. If you just do DMRG, you just get some block of numbers that gives you low energy.
And they will
it's not an isometry. But there's general procedure to convert it in 1D. In higher D, there are procedures. I don't think it's super clear what the complexity of that is in general. You can Moses move or something yeah. But I would say it differently. I would say that okay, let's just accept the restriction that we can only make isometric tensor networks. What circuits do we need to try to get close to the answer, rather than kind of variationally solving it classically and then trying to convert it to a quantum network?
But generally, it can be some channels, for example, instead of circuits. Will that?
Yeah, we're actually implementing a channel because you measure the physical qubit.
Right, but without measurements, the entire box.
Yeah, I think you would end up making a mixed state like MPO if you did that. I'd have to think about it a little bit.
Okay, thank you.
So can you say so you show the difference between the time direction and the light-like direction?
Yeah.
I didn't get why when you do it in the light direction it's better. Can you elaborate that a little?
Yeah, it's fewer qubits that you need. So if I simulate it kind of sideways, I need order T qubits. If I simulate it kind of normal direction, I need twice the Lieb-Robinson velocity times time just to get these causal cones of my correlators. I need the spatial separation between the points I measure, which can maybe give me another constant factor. And then I also need to include padding of the correlation lengths of my initial state. And this, if you start with a metal, this could be an infinite correlation length or something, or very long ranged.
And if you do it just sideways, then
then qubit cost is T.
Okay.
Order T, and plus some slope.
Thanks.
Maybe it's obvious, but you're like comparing this classical simulation versus experimental variational search, I guess.
Mm-hmm.
During the experiment, how did you evaluate the variational energy, and how did you actually change the a circuit in between?
Yeah, so I think you're talking about this one?
Right, or also the plots after, you're comparing this QMPS versus classical, DMRG, not classical, DMRG simulation.
Yeah, that is this one. So these are all simulations. None of this is experimental data.
I see.
So we use QIM, which is some Garnet, Chen's open source tensor network contraction thing, and then you just run it, find the energy, compute the derivatives, go downhill.
But maybe a few slides after, you had this the Hubbard model result. Well, right, this one. There's this plot for experiment, the simulation versus experiment.
Yeah, sure.
How did you actually experimentally do this variational search?
We didn't.
I see.
Again, we do the thing that people normally do and then try to hide, which I also did, which is you optimize on a classical computer and you implement on a quantum computer. Because doing this variational optimization in quantum hardware would, cost probably $10 million at current rates or something. Yeah, so that's a big practical problem for the community, but we don't claim to solve that. It might work better if you did it in solid state system, just because clock rate's 1,000 times higher. And,
sorry, this is a basic question probably. Can you go back to the plot you were showing the energy as a function of the number of parameters?
sorry, yes. Maybe just ask your question while I'm.
Oh yeah, sure. So my question is, I mean, you're basically doing the same thing. I'm guessing that it's basically just the MPS, but in two different forms, right? What? How can I understand that?
Yeah. So the two different things I'm comparing here is: do I treat my matrices as like a big box of numbers with no structure, or do I generate them with a sparsely parameterized quantum circuit that has, you know, one parameter or some constant number of parameters per gate, but not enough to completely specify the tensor.
I see.
And it turns out that, you know, some of this big box of numbers was not doing anything for you. So searching around in it was a bit wasteful. I think it might be interesting if people could identify classically the structure there and
yeah, I was actually going
take
to ask,
advantage of it.
does this give you a classical way of simulating?
No, it's a terrible way to do it classically because you have huge bond dimension from these circuits. And just only the number of parameters that you're keeping low. So for doing the quantum algorithm, that's what you care about. If you wanted to like use this classically, yeah, you'd have to think more carefully. It's polynomial, yeah. Yeah. So if you ask Garnet, he'll tell you you shouldn't expect an exponential speed up on ground state preparation. This won't give you, yeah. Yeah, so if you're drinking the Pepsi Kool-Aid, that's all you should ever expect. But even if that's true, there are many questions that can be addressed if you can get a ground state on a quantum computer and then time evolve it. If you have like % level accuracy on your ground state preparation, like I don't know how to compute like spectral function of a 2D Hubbard model, even if I can prepare its ground state.
And if I were to translate this into a polynomial speed up,
yeah, it's hard to translate because you also have to imagine like the cost of like measuring all these derivatives and stuff. So we do some estimates in the paper, and it's just barely eking out in the power, like if you include all that sampling overhead and stuff. I think maybe more encouraging is that it is possible to efficiently, in the asymptotic sense, prepare these with high bond dimension and reasonable depth. Yeah, Nisha?
Yeah, so even for isometric tensor network with a small bond dimension in 2D, so because you can prepare these tensor network states, but then for many of them with small bond dimension, computation of local observables is classically efficient. But then, so I don't know whether, and probably the answer is yes, the sampling problem could still be hard. Even if you can compute local observable efficiently, but maybe classically you cannot do the sampling problem measuring all the sites, whereas it seems like you can once you implement the state. So I guess I'm wondering whether you could think that you could get closer to some maybe unpractical quantum advantage. Even, I mean, sticking to small bond dimension, maybe 2D isometric states.
Yeah, I think you're saying if you include the contraction cost of the classical, yeah. Yeah, you may win by some like L to the 12th or something.
But I'm not sure about. I don't think that overlaps with the local computational basis, the broad distribution. I think that is generally into that.
I see.
Whereas in Europe, I mean, if you implement the state physically, then you just grow.
Yeah.
So in principle, even with small dimension, you could maybe not with this size. Just wondering.
Yeah, it's an interesting thought. We should think about it. Oh.
Related to asking, but do you see a way to make these things kind of practically useful?
Yeah, I mean,
I think, like for example, something like dynamics is I think it is an opportunity.
Yeah.
But it seems to me that it will be very hard to put, this approach to push it in the regime where you really sort of, if you wait for longer, then your bond dimension will
So I think what I would say is whatever you're envisioning doing with your computer, if you can do that with less qubits this way. So yeah, that's right. That's right. No,
it's just, is there a scenario, actually, maybe this tool, I want to suggest this 2D contraction could really be a scenario.
Yeah, that could be interesting. Although I think you don't expect the quantum circuit tensor networks to avoid the sharp p hardness of contracting. So you'd be looking for an intermediate case where it's like not sharp p hard to contract, but not classically efficient. And I don't know, maybe the complexity theorists in the audience have some idea what that space looks like, or if it's not empty. But yeah, it's interesting. I don't think I actually am much more bullish on the quantum materials simulation than on optimization. But yeah, because I think there's at least, kind of clear evidence for exponential advantage on calculating things that you care about in principle. And I think doing it this way would reduce the qubit resources without amplifying the coherence time you need. I didn't talk about errors here, but if you might think it's bad to do a space-time trade-off if your gates are bad. But it's actually no worse to do it sideways because you need to run the circuit deep enough to build up correlations across a correlation length. And here, the errors can't spread beyond a correlation length when you run it sideways because of these measurements. They kind of dissipate you into some steady state. And then if you have errors in there, you have instead of the error growing forever, it gives you a kind of finite error on your steady state. And if you look at it kind of either way, the maximum thing you can do is simulate something of order a few correlation lengths, just set by your gate errors. And the nice thing here is you don't have to know your correlation length in advance, and you don't have sharp cutoffs at the boundaries. So I think it could actually even be a little bit nicer to kind of run things sideways. So what I would say is it's kind of no worse to do it this way. And it clearly is better because you're putting your quantum resources towards the things that are classically hard to represent rather than just representing a ton of qubits that aren't necessarily strongly entangled with each other. Sorry, is which true? Mm-hmm.
If you can really engineer the deployments,
yeah, okay, if you can engineer a Hamiltonian and apply it in a quantum simulation sense, I think that's always going to win. Yeah. But if you want a programmable digital processor, which we could debate whether you want that or not, I think, yeah.
Could I ask a quick question about the 2D isometric tensor networks you mentioned? Mm-hmm. So I think if you want to describe topological order, you need to have only isometric on the subspace. And can your algorithm be adapted to that?
I'm not sure I understand, so maybe you should ask me offline so we can let people eat.
Okay, so okay.
That was a popular thought, I guess?
Very quick question. Okay, yes, let's postpone the questions to after the session. Okay, so thanks again for a very nice talk.